Hey, the time is 11:15 p.m. at night, and I actually did the question beforehand because I was rushing off, so it was a bit here and there. Had to pause the recording. So, uh, before I go to sleep, I'm gonna go over one question. It's a lead code medium, and it's a dynamic programming question. I'm not gonna use breadth search for my approach. So, the time and space complexity that we want is about O(n) times t and OT space. So this is a very interesting question because with OT space, right, if you look at T, which represents the given amount, you see that the amount goes up to 2, goes up to 10,000, whereas the N is a number of coins given, right? So you can add 10 coins and T is so this space can become very expensive very quickly. And if you look at the solution, it will exceed the call stack. So this is a top-down approach. So this problem will take a look at top-down usually implies depth first search, meaning what we want to do is to take the amount that we want, and then first of all we check if the basically what we're trying to do is the recurrence relation is the minimum of 1 plus the depth first search minus coin t, where there are t paths to go down. Yeah. Oh, sorry, coin n. Because n is the number of coins. Okay. So for example, if let's say you're given coins 1, 5, and 10, you can go down 3 paths. Minimum of 1 plus. If let's say I take the $1 is $11 remaining. Take the $5 is $7 remaining. $10, I'll be $2 remaining. 3 paths to go down. So let's minus away this breadth search. So this is actually O(n) to the power of t, because you go down t paths. Yeah, each time you have n paths to you have n paths to go down, and then you have to go up to t the amount times. Okay, so I believe we can memorize the steps, and truth to be told, there is a part where it says memoization. Okay, so what do we do to memorize the question? So this question, right, you are given an integer array of coins. Basically, you have a amount that you want, and you want the minimum number of coins to represent this amount. And you are given an array of coins, meaning 1, 5, $10 coins to reach 12. Right? So in the event that the amount is 0, it returns 0. That's the base case, because 0 coins make up $0. Yeah. So we create a map. This is called an amount map. All right. So amount map, basically what we're trying to do, right, is we're trying to build the problem. We look at the solution. It says top down, right? So it's a optimized version of the brute force recursion using this recurrence relation. And what we do, right, is we use a depth first search. Meaning if the sub amount equals to 0, then we have this flag that says can divide is equals to false. Right. So if the sub amount ever reaches 0, there is at least one valid combination of coins that gives you this exact amount. We can set the flag to be true. And then we return 0, because sum amount 0, as you mentioned before, takes 0 coins. So if the amount map has this sub amount, then we will just get it, because that's the part where we memorize it. And then we'll build it up using this for loop. So the minimum is actually an array of coins. So I use a higher order array function to map through. If the sub amount minus the coin is let's say $10 minus $5 is more than 0, then I'll take $5 and then I'll return the search of $5, because I already subtracted 5. So if it's less than 0, what does this imply? The coin is bigger than my sub amount, I can return infinity, because it won't be a valid option, and math.minimum automatically skip infinity. Okay, then I will do amount map dot set sub amount minimum. So this sub amount is basically telling you that to reach this sub amount of money, what's the minimum number of coins needed, because you already did the DFS here, and then we'll return minimum upwards. So what this does is it will go through, if let's say you have $12, right, in this example, you'll go through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? And you'll map all of them in the amount map. And then it'll tell you that to reach $12, you need 12 coins. And then we'll map through the different coins. If let's say I take, instead of taking, let's say, 5 $1 coins at the end, I will take 7 $1 coins and 1 $5 coin, and then I will get a smaller amount. And of course, this DFS will keep running, just that it's memoized, and the time complexity is still there, but you will have a lot of recursion going on, especially if let's say you have an example of like, let's say 9999, which means you will take $1, 900. You call the recursion 9999 times, which is very expensive. And even though this in theory still works and it's quite efficient because of the memoization, it is going to not be allowed in this specific question because of the call stack being insufficient. So another approach, so this one we'll call it the top-down approach, EFS. So there's another approach, which is a iterative approach. So this is the recursive approach. It makes more sense recursively because the recurrence relation is a very smart way to do it. It's saying like, if I take this path, if I take this path, if I take this path. Another way to do it is if all the coins, we will use the iterative method. So we'll create an array, amount array, where the array is of size amount plus 1. Because if it's a size amount, right, the final index will be an index amount minus 1. Because arrays are inherently zero-based. So this is not, we need to add one more so that we can find out how many coins we need at that specific index. Okay. And then what we will do, right, is to say that we will fill it up with amount plus 1, meaning amount plus 1 is our maximum instead of using something like infinity. Yeah. So we don't want to use infinity because we might have some overflow issues. So fill amount plus 1, because the logic is even if we take all $1, which is the smallest amount of coin, right? Coins, yeah. The coin can go up to what is minimally $1. So amount plus 1 will always give you more than amount. So that's important for the return portion. Yeah. So what we do is for let I equals to 1, I less than the amount, plus I will look over the coins and I'll say if coin is less than equals to I, right? Then what I will do is at this amount, right? At let's say index 1, index 1, to make $1, I will take the amount at the array itself, which is amount plus 1, which is 10,001. If let's say the example is $10,000, or 1 plus the amount at the end, which is still at the maximum amount, which is why we don't want to use infinity, right? Because we will add 1 to it, which is why using this is appropriate, right? And then this will keep updating backwards, right? Because what I'll do is, if let's say at $2, what will I do? I will, or let's say at $5, right? So we'll just look through an example. Console.log amount array I. Right, we'll run the code. Then we look here. So for $11, the amount of array I will be 1. Okay, because to reach $1, right, what I will do is I will either take $11 plus 1, which is $12, or I will compare it with, okay, maybe I'll just log it above that, okay, so you can see. So we will use, if this coin's value is less than the amount, less than or equals, equals you can, because 0 is the base case, so equal is okay. So index I is I dollars. We'll use the smaller I, which is I minus coin to build it. Okay. So you can see that amount array is initially $12 because it's 11 plus 1. And then we'll compare with 1 plus amount I is 1, coin is $1, 0. Okay. Then at $2, right, you will compare $12 versus 1 plus 1. So it's $2. Okay. Then later you will take $2, compare with 1 plus amount array I minus coin. But coin now is $2 because now you have $2 coin. So you're comparing two $1 coins versus one $2 coin. You will take 1. So to reach $2, the minimum amount you need is 1 coin. Yeah. So we'll just keep carrying on. And for $3, yeah. So for 3, you can see that at this point, you will look over the second coin because $3 can be made out of 3 $1 coins or one $1 and one $2. So obviously to make $3, the minimum is $2, 2 coins. I mean, yeah. Then we'll keep going forward. And at each case, right, for each amount P, you can have to n tries, n coins to check whether it's permutable. So this gives you a very neat solution. And it only incurs O1 space on the call stack. So yeah, it does not cause any overflow. Whereas, okay, so maybe I'll hide this and then we'll just change it to wood clean. And then we'll remove this and then we'll run. So you'll see that even though it passes theoretically all correctly, right? The fourth case where you have 9, you have too many stacks being called, which I believe in this case it's NT, which is not very efficient. Or even if it's T, right? Yeah, the number of call stacks will be too high. Especially if let's say you're using a LeetCode platform where you have to conform to their time and space complexity. So yeah, I will just change this back. Set this as my final solution, and we're done.